A very good morning to all. It is our great pleasure to welcome you all to the Knowledge 4.0 webinar series, which is one of the unique and distinct initiative of Chennai Institute of Technology under the guidance of our Honorable Chairman, Sri P. Sriram, who is one of the well-known first-generation entrepreneur, industrialist, managing director of MK Group of Companies. Under Knowledge 4.0, we have been conducting webinars such as technical webinar series, research webinar series, career guidance webinar series, and innovative talk webinar series. Apart from the regular webinar series, we are also conducting international conferences, national seminars, international seminars, and workshops and faculty development programs. So far we have conducted more than 140 webinars, and soon we are going to reach 150 webinars. And these webinars are highly to enhance the knowledge of faculty members, researchers, and students community during this lockdown period. Today we have Dr.G.KUMARESAN, Professor of Mechanical Engineering and also Deputy Director of Research, CFR Anna University, to deliver the lecture on Fundamentals of Computational Fluid Dynamics and a technical webinar series. It is my great pleasure to welcome him for this wonderful forum, sir. Welcome, sir.
Thank you. Welcome.
Yes. And Chennai Institute of Technology was established in the year 2010 by our Honorable Chairman, Sri P. Sriram, and today we are being within top 10 among all our private engineering colleges in Tamil Nadu. It is my great pleasure to welcome you all the participants and our today expert, Dr.G.KUMARESAN sir. And now I request Ms. Swapna Sri, student of second year Mechanical Engineering, to introduce our today's expert. Please, Swapna.
Good morning, everyone. Myself, Swapna Sai, pursuing second year Mechanical Engineering in Chennai Institute of Technology. Today is our expert, Dr. G. Kumaresan. Dr. G. Kumaresan, Associate Professor from Anna University, did his BE in Mechanical Engineering from AC College of Engineering and Technology, Karaikudi in the year 1997, and ME in Design and Production of Thermal Power Equipments from NIT Tiruchirappalli in the year 1999, and PhD in Solar Thermal System from CEG Anna University. He was a lecturer for 6 years and then became Assistant Professor Senior Grade from the year 2008 in CEG Anna University, and is now the Deputy Director in Research under Center of Applied Research. He has completed 6 research projects and has published more than 40 international journals and conferences. His subject of expertise are gas turbines, gas dynamics, thermal engineering, and thermodynamics, and solar thermal. We welcome you, sir.
Okay, so let's start my lecture.
Please, just a record of your sessions.
Yes, sir. Okay. Is it visible?
Yes, sir. Please turn the screen share on, sir. It is not yet visible. No problem, sir. Please select turn on screen share and click NDA screen, then put share.
Just a minute.
No problem, sir. Please do it comfortably.
Now, is it visible now?
Yes, sir. Yes, sir. Please go ahead, sir. This is good, sir.
Yeah. Okay. Fine. Very good morning to one and all. Before start of my lecture, I would like to convey my sincere thanks to the management of CIT for giving this opportunity to share my expertise in the domain of computational fluid dynamics. So the title actually the fundamental of compressible computational fluid dynamics. This is simply called as CFD. Okay, but here my title shows CFD analysis of thermal systems. Though it is the title, there is a mismatch. But I'll start with introduction aspect of CFD. Then later on, I will move on to what are all the research activity which I have performed in the field of CFD. I would like to share in this forum. Okay, so this computational fluid dynamics, this is nothing but numerical. So to simply say about to understand even on layman style, this is nothing but numerical simulation of free flow heat transfer. So wherever there is a free flow with the heat transfer, not only heat transfer, mass transfer, or simply call it as a transport phenomenon. So for any kind of transport phenomenon where it is possible to analyze those kind of problems with the help of a computational method that is called as a computational fluid dynamics. But the name, though it shows a fluid dynamics, it doesn't mean that this method capable to solve only the free flow problem. But this computational fluid dynamics capable to solve any kind of transport phenomenon related problems. That is the quite advantage of CFD. So this CFD, which is widely used in many industrial segment, because it gives a lot of benefits that is listed here by using the CFD, where the effective design of engineering system which is possible, and we can simulate what are all the ideal conditions which is not practically possible and feasible. Those kind of ideal conditions it is possible to simulate by using a computational method, which gives complete information. So by applying a CFD method, it is possible to get the complete information for a given problem. That is the another quite beauty of this subject CFD. So of course this the help of CFD, it greatly reduces the total effort needed in the laboratory, and also when compared to experimental analysis, CFD, which is cheaper in many cases. So these are all some of the important advantages of computational fluid dynamics. But is it inevitable? CFD is inevitable, not necessary. We can even go for experimental fluid dynamics called as a EFD, and theoretical fluid dynamics at TFD. So I could say CFD, this is the complement between EFD and TFD, right? In order to gain the advantages listed here, effective design, impossible conditions also, where we can analyze by using the computational method complete information for a given problem. So we can reduce our time as well as the cost, everything with the help of a computational method. These are all the advantages. So we can use CFD before start of any experimental fluid dynamics. Okay, to become master in this subject, computational fluid dynamics, where we should know basics or fundamentals of these three important subjects. One is fluid dynamics, then numerical methods, heat transfer. Because as I said, computational fluid dynamics nothing but numerical simulation of flow and heat transfer, as well as mass transfer. So if you want to become master in this subject, you should know basic aspects of or basic knowledge of fluid dynamics, numerical methods, and heat transfer, even mass transfer also. Not only that, after gaining enough knowledge from these three different subjects, if you would like to apply this CFD concept in specific application like combustion or mass transfer with the phase change phenomenon, melting and solidification, rotordynamics, turbo machines, heat exchanger, aerospace, automotive. So for different applications, if you would like to apply CFD, so you should know basics of in the respective field. So after gaining knowledge from these three main subject, where we can apply the computational fluid dynamics concept, the various engineering domains to solve engineering problems. So that is the knowledge prerequisite for this subject. Okay, so this is CFD. As I said, this is a complement between EFD as well as TFD, but each method, CFD or EFD or TFD, each method having its own limitations, or each method having its own merits as well as demerits. Before start off computation fluid dynamics, let me quickly cover the details of the advantage and the drawback of the EFD as well as the TFD. So experimental investigations, often there is actually no substitution for experimental fluid dynamics, because conducting our engineering experimental study, which gives more information when compared to theoretical method or numerical method. But there are a lot of drawbacks behind the experimental investigation. The one is which is very expensive. So to conduct any experimental study, first we have to build develop a experimental, fabricate the experimental setup. So this is expensive in most of our research-oriented applications. So this is expensive. Sometimes which is impossible. Some kind of experimental study which is logically not possible to do those kind of experiment on the laboratory level. And moreover, in experimental study, it involves a lot of measurement. Yeah, lot of measurement errors. Yeah. My voice. How about my voice?
Yeah, now it is okay.
Is it okay?
Now it is okay, sir. Now
Yeah.
Yes, sir. Excellent.
Okay, fine. So the experimental investigations, there is a good advantage. Actually, there is no substitution for experimental investigation, because where we can get more information through the experimental analysis. But there are some drawbacks. So the experimental investigations we can do in two different mode, either full scale mode, or we can go for the scaled model. So whether it is full scale model or scaled model, it involves a measurement error, because while conducting experimental investigations, it involves a lot of instruments to measure various parameters. So every instrument offer some error. So this is one of the drawback in experimental investigation. Apart from that, it gives more information when compared to theoretical method as well as numerical method. So whether it is a full scale model or scaled model sometimes it is essential. We cannot conduct a full scale model. Say for example, if you want to develop the flow analysis over a Eurofile, I mean aircraft wing, it is impossible to develop original aircraft wing. At the time we can go for scaled model. So this is scaled model fabricating scaled model. This scaled model.
Sir, sorry to disturb you. Yeah, sir. Now
tell me.
Okay, sir. Now it is okay. Sometimes it is getting disturbed. Now it is okay, sir. So please talk like this, sir. So
okay. Yeah. Okay. So,
yes, sir.
Okay. So this involves whether it is scaled up model or scaled down model, which is sometimes it is difficult to extrapolate the results for our original size. That is one of the main drawback of this experimental investigation. Apart from that, where experimental investigation, which gives a lot of insights about our science and technology, then next analysis is actually called as a theoretical fluid dynamics. So this is nothing but solving problem by using analytical method. That is called a theoretical calculation. But the drawback actually exists that analytical the formulas available only for a few cases. Sometimes it is very difficult to develop the formulas of our original research oriented problem. That is the drawback of theoretical calculation. Coming to numerical method, our computational method. So this solution for computation using computational method for any engineering problem, which is easily possible for whatever the kind of problem, whether it is whatever the complexity involved in engineering problem, it is possible to get the solution by using the computational fluid dynamics concept. So that is the advantage. It's a very cheaper, as it is indicated earlier, where we can get more information, whatever the complexity involved, it is capable to solve by using the computer computational fluid dynamics concept. That is the advantage. But the drawback, of course, here also there are some noted drawbacks. The first drawback, it deals with a mathematical description, not with reality. So it solves finally only the governing equations. So the governing equations are useful to describe the physical phenomenon of a given problem. So it deals a mathematical description, not with reality. That is one of the drawback. The other drawback, actually, for a given problem, the multiple solutions are possible in CFD method. So as an engineer, so we should know what see which solution which is more closer to our benchmark solution. So this is called as the validation. So we should always validate CFD results. So the validation which is possible either by comparing with the experimental results or by comparing with some analytical results. So this is without validation. So it is very difficult to quantify our CFD answer. So that is the drawback of computational method. Apart from that, this is very cheaper most of the situation when compared to experimental investigation. So there are many numerical methods are available. There are three different this is CFD which works based on the discretization technique. There are three different discretization major three techniques are finite difference method, finite volume method, and finite element method. So it is very important thing to note here that many of the softwares available available in CFD programs which is written based on a finite volume method. Almost 80% of the software which is written based on finite volume method. So that is the advantage of finite volume method when compared to other kind of method. So there are different techniques possible in CFD: finite difference, spectral method, boundary element, vorticity. So there are many techniques, but majority of our CFD related softwares which works based on finite volume method. So I will try to focus my lecture towards on finite volume method. Rather than finite difference and finite element method. So these are the limitations. Actually, the limitations of CFD. This CFD solution, which is mainly based on the physical model of the real the given problem. So I mean, whatever the model chosen in computational method, say like whatever that. Like say for example the turbulence, the compressibility, and the multiplication. To solve a turbulence related problem, there are many models are available. So which physical model capable to solve a given problem, that information is very much important. Otherwise we will end up with a wrong answer. So we should understand what are the physical models are available in computation field method. So by carefully choosing those physical model, it is possible to come up with somewhat a good answer by using computational method, right? That is the one of the limitation. The other limitation, as like in experimental method, measurement error, that is a major problem in experimental investigation. Here also there are some errors involved in numerical method, that is called as a round off error and truncation error. So these errors are inevitable in CFD. So that's why by solving problem in CFD where we can get only the approximate answer, it is impossible to get accurate answer by using a computational method, because it involves a lot of error, like the round off error and truncation error. These are all simply called as a numerical error. And other limitation, actually boundary conditions, like to solve to solve our engineering problem using computational method, we need good boundary condition and initial condition to define a particular problem, right? So improper selection of or improper use of boundary condition, initial condition, which may leads to wrong solution. So we will end up with the wrong conclusion. So we need to understand the physical problem very clearly. Based on the physical problem, we should arrive what are all the appropriate boundary conditions and initial conditions are normally needed to solve transient problems. But for steady state problem where initial condition does not require. So by using those conditions where we can really solve any kind of engineering problem. So when you fail to understand this physical model, numerical error, boundary conditions, so definitely we will end up with only fair answer. So it is impossible to justify or validate our CFD answer with benchmark answer. So we should take care about these information. So where we can use CFD. So like the CFD, this concept, the CFD concept was initially started with the aerospace industry in the late of 1970s, where people aerospace industry, they started to enjoy the benefit of CFD. Nowadays almost all the industry, they are enjoying the benefits of CFD, like so automotive industry, the aerospace industry, where we can develop a good aircraft wing, where we can develop a good aircraft engine of the help of CFD. For automotive applications, as you can see, a flow past your car, like how much the drag was experienced by the car because of its shape, everything, where we can analyze here also, where we can analyze the flow over car, flow inside of the car. I mean the cooled air inside of the car. This can be analyzed. The recent advent of the recent use of a CFD in our society as biomedical applications, like in biomedical also where CFD. So this is the like the laser treatment application. This is our high picture which is shown here. During laser treatment, how much amount of heat actually penetrated in human body, this can be captured with the help of CFD. In chemical processing also, where we can apply cyclone separator shown here to understand how the flow, how these large particles settle down at the bottom of the cyclone separator. Likewise, where we can use different chemical applications, where we can use this computational method, and HVAC applications, like a person operating computer, like how this cool are distributed. Okay, so there are large number of computers housed in a common room, where the more heat is generated, and how much amount of coolant air is required, and how about coolant air distribution inside of the room. There are large number of computers housed, everything, where we can analyze that way, where we can properly size the HVAC system by using the CFD and the hydraulics application, like the gate release from the water from a dam, so that how this stored energy which is converted into the kinetic energy, this can be analyzed by using CFD. And the marine application, the shape of the ship can be analyzed, and the turbo machine application, where you could see the rotor and stator. So these are all the blades, how the blade shape will be for better energy extraction from the fluid, or better energy transfer to the blade. This can be analyzed, how many number of blades, and what is the spacing between the blades.
Sir, are you able to hear me, sir? Sir, are you able to hear us? Sir, are you able to hear from me? Participant, please be online. Just a minute. Some technical issues. One second.
Hello.
Yes, sir. Sir, are you able to hear from us?
Yes, sir. Can you hear my voice?
Yes, sir. Now it is okay, sir. Now it is okay, sir. Suddenly the connection got lost. Sir, please. Now
okay.
You can go for screen.
What about my screen?
Yeah, now we can share your screen, sir. Now we can share your screen.
Yeah. Okay. Sorry.
No issues, sir.
Hello.
No issues.
Sorry. Yes. Okay. Sorry for the technical issue.
No
okay. So this CFD, yes, CFD application can be extended for various engineering applications, as I as I listed, aerospace, automotive,
sir,
biomedical, chemical processing. So yeah.
Sir, sorry for the disturbance. Sir, now
is it okay now?
Now please go for screen sharing, sir. Now screen is not visible. You can once again go for your screen sharing.
Excuse me, sir.
Yeah.
Your voice we can able to hear, sir, but the screen is not visible, sir. Your presentation is not visible.
Yeah, now please minimize. Yes, sir. Now maximize it, sir.
Yeah, sir. Now fine.
Yeah. Okay. Fine. Yeah. Okay. Again, sorry. Okay. So we can use this CFD concept for various engineering applications. There are some applications which I have listed here, where this industry really enjoying the benefit of the CFD. So this CFD, where we can understand in two different aspects. One is theoretical computational fluid dynamics, and the other one is straight away by using the software, how to solve engineering problem by using the computational method. So there are two different ways: theoretical understanding of CFD and software understanding of CFD. But my suggestion, actually, first we should gain the information about theoretical fluid dynamics. I mean, see what are all the technical informations terminology involved in CFD. By gaining enough information about the theoretical background of computational fluid dynamics, then when we use a software where we can effectively use the software to solve our engineering problem. So that is for any engineer, we should study the textbook written on computational fluid dynamics. Then we'll move on to the software. So that is which gives really more insight about computational fluid dynamics. But here this scheme which shows how to use software for the CFD to solve engineering problem by using the computational fluid dynamics method. So this to solve our problem by using software, it typically involves three important steps. It starts from pre-processor, then the solver, then the post-processor. Okay, in pre-processor, it includes a lot of activities. The one is creation of geometry. To solve any problem, first it is essential to develop a model that is called a creation of geometry, where we have to go for mesh generation, right? Then we have to identify the material property of the given engineering problem. Then we have to feed appropriate boundary conditions for a given problem. So these activities are generally called as a preprocessor. Then the next step actually solver. In the solver method, where we should identify what are all the transport equation. Okay, see, there are by solving the engineering problem by using software, generally where we can come up with the various variables. Like there are 7 engineering variables. Normally, 3 variables, velocity variables, say UV, then temperature, then pressure, then density, then internal energy I. Right? There are 7 variables. So to solve to get all these variables, definitely we need equations. So this to get velocity component UVW, so we should use a momentum equation, and to get density we should use continuity equation. To get temperature we should use energy equation. To get pressure, internal energy, we should use the equation of state P equal to rho RT, I equal to CVT. So by using all these equation, where we can get all the variables, so in software all the equations are available. So our duty as engineer, our duty is to enable appropriate equations to solve a given problem. Like when you click momentum equation, right? So where you can come up with variables of velocity component. So when you click energy equation, where you can come up with temperature or enthalpy. Likewise, where you choose transport equation, right? This transport equation definitely used to get the variable. Then the physical model also very important. Like to solve a flow related problem, like there are various turbulence models are available. Like by using appropriate turbulent model for a given problem. So like there is a standard turbulence model, K epsilon model. There are different K omega model available. There are different turbulence models are available. So the proper understanding of turbulence model to solve a given engineering problem, which is paramount importance. So by selecting appropriate turbulence model, where we can come up with a good approximate answer from CFD method. So by clicking transport equation, physical model on the solver settings. So after enabling all these equations, like then the next we have to get the solver setting. So in the solver settings, where we can feed the information about convergence criteria. Like say in the convergence criteria, if the solution is converged, like these informations are now will appear in the screen, right? So these convergence criteria, where we can this information that we can give to the software accordingly, where we can get a precise answer from the software. So these are all the options available in the software. By clicking those options, then the software will take all the information, and the software will run the program. Finally, that you get the answer. Once the solution is converged, that you can get the answer. So checking answer from software, that's actually called as the post processor. So in the post processor, where whatever the information you want, you can get in the form of contour, you can get in the form of velocity, vector. So the different profiles it is possible to obtain from the software, right? So this is how to solve problem by using software. But when you solve problem in CFD method using theoretical method, right? It really involves some different method, like where you need not to create a geometry, but rather where for a given problem where we need to divide the domain into a number of subdomain. So now we have to solve governing equations, I mean the transport equations for each and every subdomain. Then finally we will get the answer. I mean answer in the sense we will get the variables by solving a governing equation for each and every subdomain. That is the theoretical CFD. So in theoretical CFD procedure, somewhat different when compared with the solving problem by using the software, but the basic the method remains same. But in software there are many features are available. So where we will, as far as possible, it is possible to solve even very complex problem by using the software when compared to solving problem by theoretically, right? So here some simple example actually given. A liquid filling in a bottle, that is the problem. So the bottle actually divided, so the whole bottle which is divided into a number of subdomain. So you could see the grid. So this is the whole domain which is converted into a number of subdomain. Then we have to identify what are the governing equations for this fluid filling in a bottle. So after writing the governing equations, we have to convert. So normally in CFD, what happens? The domain converted into number of subdomain by using the mesh. We have to identify the governing equation, solve the governing equation for each and every subdomain. So in software, where the software which is capable to solve only the algebraic equations when compared to the partial differential equations. So there are many equations, transport governing equations like continuity equation, momentum equation, energy equations, all the equations available in the form of partial differential expression. So this is a computer which is capable to solve algebraic equation rather than partial differential equation. So in computer, what happens? There is a procedure. All these partial differential equation successfully converted into algebraic form. Once it is converted into algebraic form by using the numerical method, where we can solve the algebraic equation. Once the algebraic equation solved with the help of numerical technique, finally where we can come up with the variables. It could be temperature, it could be velocity, pressure, or whatever the variable we want. It is possible to solve by solving algebraic equations. Algebraic equation, which is the conversion of approximate representation of our governing equation. That's why in CFD it is impossible to get accurate answer, because we are not going to solve partial differential equations straight away. We are going to convert into partial differential equation into the algebraic form with a certain approximation. Thereby, so by solving this algebraic equation, we'll get only the approximate answer. But as far as possible, it is our duty to get our approximate answer somewhat very closer to that benchmark answer, right? That is this is what happens in CFD. So these governing equations are converted into the algebraic form. So these algebraic equations, the systematic equations, are solved by using the software, so that where we can get all the variables at the end of convergence. Okay, so whatever the problem, right? This is a standard generalized transport phenomenon equation, where in this equation, where the phi actually replaced as a u, v, w, or h, or 1. Accordingly, this is called as a momentum equation, energy equation, and continuity equation. So we need to solve this governing equation by substituting by replacement of appropriate phi in this equation. Once this equation solved with the help of integral method, so the finite volume method, which is also called as the integral method. So by using this finite volume method, it is possible to convert this partial differential equation into the algebraic equation. So finally, where we can solve this algebraic equations with the help of the numerical method. Okay, so this is this diagram which gives the whole domain which is converted into subdomain. So for a subdomain where the centroid of the subdomain denoted as letter P, whose adjacent centroids are labeled as caps letter W and caps letter E, we have to apply governing equation for this subdomain, then convert solve this governing equation, and convert this governing equation into the form of AP, 5P, AW, 5W, AE, 5E, and the source term. So where P stands for present centroid, and whose this centroid bounded by west side centroid and the east side centroid, and AP, AW, AE, these are all coefficients. So by converting this differential equation into this blue color equation, this is called our final discretized equation. By solving this discretized equation, so based on number of subdomains, if there are 5 subdomains, we will end up with 5 discretized algebraic equation. By solving 5 algebraic equation, where we can come up with variables for each and every centroid. Okay, this is the way how the CFD solves our engineering problem. So first we have to consider a domain. This domain converted into a number of subdomain. Then say by using CFD, we will get answer only at the discrete locations, not at the whole domain, only at the discrete locations. So for that, every subdomain or every grid mesh where you apply this governing equation, then convert governing equation into algebraic form and solve the algebraic equation with the help of numerical method. Finally, where we will get all the variables, engineering variables, right? Okay, this is the basics about CFD. Okay, there are some research work which we performed in our institute. That research work I would like to share in this forum. The first research work which is solar cooking, development of double-walled solar cooking unit. That is one of the CFD work which I have performed. Okay, so here before discussing about the CFD for development of cooking unit, so here I'll show you the significance of the development of cooking unit. So here there is a double-walled cooking unit. So we conducted a computation analysis about the efficient of this double-walled cooking unit. For the double-walled cooking unit, there is one inlet, there is one outlet. So for this inlet where the hot oil circulated, the foodstuff which is kept here, so it looks like a tawa. So normally tawa which is used to prepare for frying application for any foodstuff, if you want to fry, right, where we can use the tawa shape cooking unit. The same tawa model simulated here. So for this tawa model where the hot oil circulated here, this hot oil transfer the energy to the foodstuff, then this less energy oil from the cooking unit which is again goes to a tank where picks heat energy, and in this way the hot oil continuously circulates into the cooking unit. So we would like to know how much inlet and how much outlet. As per the diagram, there is one inlet and one outlet. We would like to know for the tawa shape double-walled cooking unit, so how much the outlets are required to quickly transfer energy from hot oil to the foodstuff. That is this analysis which we performed by using the computational method. So here the diagram which shows the tawa cooking unit, we conduct, as I said, for most of the computational analysis, we need validation. So after conducting a computational analysis, we conducted experimental analysis and we validated our computational results along with the help of the experimental results. So for which, so we have identified the boundary conditions. As I said, boundary conditions are very much essential. Proper boundary conditions are very much essential to solve engineering problem. So we identified boundary conditions and we identified and we enabled the governing equation continuity. Since this is a flow with heat transfer, continuity equation, momentum equation, energy, 3 equations are enabled. These are all automatic available in software. Our duty is to just click those equations. Then the model has been created. So this model consists of one inlet and one outlet. So to get a good answer from computational method, we have to conduct a grid independent study. So this study which gives how many number of measures are required to solve a engineering problem. So as I said the very beginning, for a given engineering problem, there are multiple solutions are possible in CFD, right? So it means, say for example, to solve this tawa model, so when you consider 10,000 mesh, you will get one answer. When you consider 1 lakh mesh, you will get some different answer. When you consider 5 lakh mesh, you will get different answer. Okay, so for different number of meshes, eventually we will end up with different answers. So my question is, how many number of meshes are correct to get a somewhat good answer, right? For which that study actually called as a grid independent study. So we need to vary the number of measures for a given problem. So when you vary the number of measures, definitely you will get different answer beyond a certain number of measures. Okay, that is what shown in this picture. On x-axis, the number of measures are taken. On y-axis, heat transfer rate taken from the software solution. So by considering less number of measures, so say it started with 10,000 mesh, 10,000 mesh, there is some different heat transfer rate. So by keep on increasing the number of measures beyond 5,20,000 mesh, even for 6 lakh or 7 lakh or 8 lakhs, beyond 5,20,000 measures, there won't be any change in heat transfer rate. But less than 5 lakh, you see that there are different heat transfer rate because of a different number of measures. That's why, so when you vary the number of measures beyond a certain number of measures, there won't be any significant change in the output. So where we have to freeze the number of measures. That study actually called as a grid independent study. So this study is very much essential to freeze the number of measures to solve for a given engineering problem. So for this problem, which I have identified 5,20,000 mesh, so after freezing the number of mesh, where I extended this analysis by consisting various number of outlet. So for the diagram, one inlet, one outlet shown. Okay, here you see that one inlet, the results are taken, temperature results are taken from the analysis. One inlet and 2 outlet and 4 outlet, right? So for different number of outlets, there are different heat transfer rate, and that is what plotted here. For there are 3 colors, blue color, red color, and green color. So the blue color stands for single outlet, then 2 outlet for red color, green color for 4 outlet. So when the hot oil admitted into the cooking unit at various velocity, when I vary the different velocity, whatever the difference in velocity, the 2 outlet configuration capable to transfer more heat from the hot oil to the foodstuff when compared to single outlet and the 4 outlet configuration. So we freeze that from this analysis, it is where we concluded that 2 outlet configuration capable to solve to transfer a good amount of heat to the foodstuff irrespective of the flow velocity, right? So as I said, the validation is very much essential. So we have conducted an experimental study in addition to computational study. So the one result actually, the y-axis shown on the heat transfer rate, primary y-axis, and here the top line for the experimental study and the bottom line for the computational study. So the change of heat transfer rate when the time progresses in CFD study, which is very much the trend of a change in heat transfer rate is very much similar to that experimental study, and moreover there is a less difference in heat transfer rate between computational result and experimental result. In this way, where we justified whatever the measures opted for a given problem, whatever the solving procedure considered this problem, which is validated with the help of our experimental study. So in this way, where we validated the study. And there are many pictures shown here to understand how much about the temperature, change in temperature, and everything reported in that paper. Then another paper where also we performed a numerical study, but this study actually for flat plate cooking unit. The earlier study for tawa unit, and this is for flat plate cooking unit. So you could see here the diagram, the picture taken. One is tawa cooking unit. That earlier paper covered the information about development of efficient tawa cooking unit, and this is the flat plate cooking unit. By using this cooking unit, it is possible to prepare foodstuff like dosa, chapati, everything where we can prepare by using flat plate cooking unit. For this study also, where we performed a computational study, so for which the domain, so this is the CAD model taken here. First we created the geometry. Then after creating geometry, then the mesh is adopted for that CAD model. So here there is a hot oil. So again, this is also the double walled flat plate cooking unit. There is a gap here, the foodstuff placed at the top of the cooking unit. So in this gap, hot oil circulated. So once hot oil flows through the gap, heat is transferred from the hot oil to the foodstuff which is placed over the cooking unit, right? That is the problem considered in this paper. This problem solved by using CFD based software. So the results are shown here. When the heat transfer fluid admitted into the cooking unit at various temperature, right? So this is the entry and this is the exit. The center side where the foodstuff which is placed, since the foodstuff placed, like say for example dosa butter poured at the center side. This since the dosa butter poured at the center side, this dosa butter taken good amount of heat from the hot oil, so that the heat transfer taken place from the hot oil to the foodstuff. So the for different entry temperature where the heat transfer temperature which is estimated, calculated on the heat transfer also, which is heat transfer rate also evaluated. This heat transfer rate validated by using experimental method, experimentally also by using this experimental setup where we conducted experimental study and we compared our experimental study with the computational study. So these are all the computational study. And this is our average experimental study. The average result shown here. This average result, which is same as the almost same as the average of 3 experimental computational study performed for this analysis. In this way, where we performed our developed double-walled flat plate cooking unit, which is capable to deliver enough heat to the foodstuff by considering various boundary conditions, various discretization procedure adopted in this paper. For rest of the information, so you go through this paper where you can get more information about the CFD information about how to solve flat plate cooking unit. Then other work which we performed about heat exchanger by using computational method. So in the heat exchanger, where the normal heat exchanger consists of baffles, so the baffles are used to change the shell side fluid flow direction. Thereby, the resident time of shell side fluid increases greatly in heat exchanger, so that the heat transfer takes place from shell side fluid to the tube side fluid or vice versa. So, but the vertical baffles which create a major drawback about more pressure drop. So we have taken this problem in this analysis, CFD analysis, instead of vertical baffle. So we considered inclined baffle. Inclined baffles like here I'll show you the inclined baffles. Yeah, so this is vertical baffle, right, in this picture. And this is the inclined baffle. So as I said, the vertical baffles create more pressure drop, but the heat transfer rate is more. So that is, but though the heat transfer rate is more, the penalty is more pressure drop. So we want to tackle this issue. I mean, see, to get more pressure drop, but at the expense of less pressure drop. So we went for an inclined baffle. For the inclined baffle, where we considered various inclination angle. We want to know what the inclination angle is better to get more heat transfer rate, at the same time less pressure drop, for which we considered four inclination angle. So 25 degree, 30 degree, 35 degree, 40 degree, 4 inclination angle. 0 degree means vertical baffle, I mean conventional baffle, right? So, and also we varied the baffle cut. Baffle cut, which is nothing but there is a gap provided here in the baffle. Here you could see very clearly. So this is the baffle plate, and the portion, some portion which is removed off from the baffle plate, that is called the baffle cut. So more small baffle cut and large baffle cut creates a lot of problem. So ideal baffle cut, I mean proper spacing, right? That is very much essential to get more pressure drop. At the same time, to get less pressure drop, at the same time more heat transfer rate. So that optimal baffle cut already where the people identified for conventional baffle, but for inclined baffle where we want to know what is the optimum baffle cut, for which we have taken other information, that's 25% of baffle cut, 30% of baffle cut, 35% of baffle cut. So we considered these different cases, different inclination angle, different baffle cut, and we compared, we analyzed pressure drop and heat transfer rate. We compared this pressure drop and heat transfer rate for our conventional baffle. So finally, where we proposed best combination of inclination angle and baffle cut, right? That is what performed in this study. So for which where we identified the governing equation and the boundary condition of the physical, I mean the heat transfer heat exchanger geometry, which is taken into the taken from that paper, and a model has been created and went for meshing, and we analyzed for various inclination angle and buffle cut. Then finally, where and in this paper where we reported what are all the properties taken into the account, what are all the assumptions invoked for this problem, everything reported in this paper. We'll quickly see only the results. Okay, so the diagram, top diagram shows vertical baffle, and other rest of the diagram shows inclined baffle for pressure drop. So this diagram shows a pressure drop for various arrangement. Inclination angle of 0 degree to 25 degree, 30 degree, 35 degree, 40 degree for various inclined angle, where pressure drop taken, and temperature also taken by using the temperature distribution, where heat transfer rate also evaluated, and finally and the velocity vector also, which is taken from the analysis. So that's why I said by using CFD it is possible to get the complete information. But when you do all these analysis by using experimental method, we need a pressure drop individually, we need temperature drop individually, right? We need a flow meter individually to get all the answer to all these velocity, pressure, and temperature. We have to rely upon the individual instrument. But in CFD, where by using one physical geometry and measured geometry, it is possible to extract all information. So that's why complete extraction of complete information, that is the good advantage of the CFD. So by using this velocity information, temperature information, and pressure information, where heat transfer rate which is taken, this heat transfer rate which is plotted here. So these are the results obtained from a computational method. So these results which shows, as I said, different angle, inclination angle, which we have considered in these analyses, and different baffle cut also which we have performed. 25%, one is for 25, other one is for 30%, and the third one is for 35% baffle cut. So this is for 0 degree, 25 degree inclination, 30 degree, 35 degree, 40 degree. So the top diagram which shows a pressure drop across the heat exchanger. Then the middle diagram shows a temperature drop of shell side fluid across the heat exchanger. The third diagram which shows heat transfer rate between shell side fluid onto the tube side fluid and heat exchanger for various baffle cut and inclination angle. So from these three chart, where we can safely conclude that the combination of 35 degree inclination angle and 30% baffle cut, which provides more heat transfer rate, but at the same time less pressure drop. But other cases, though the heat transfer rate is more, pressure drop is also more, but that is the penalty, right? So we optimized that 35 degree inclination angle, 30% baffle cut, which gives somewhat more good heat transfer rate, at the same time less pressure drop, right? So okay, when you do this analysis in reality, we have to fabricate heat exchanger for various combinations. We have to fabricate at least 8 heat exchanger. Yes, because we have to fabricate conventional baffle, 25 degree inclination angle, so 5 heat exchanger, but different inclination angle, and 3 baffle cut, variants of baffle cut. So we need 8 heat exchanger plus 1 conventional heat exchanger. So it is very highly impossible to construct a heat exchanger by considering all these aspects. That's why by using this CFD analysis, first we can solve the problem for various combination, whichever combination where we feel good result, favorable result. For that combination, it is enough to fabricate our final original model. So for that final model, where we can fabricate and we can conduct experiment and we can compare our experimental results with the computation results to validate our CFD answer, right? So this is one of CFD work which we have performed in heat exchanger. Then another work which we performed using CFD for phase change problem, right? So for phase change problem, where we taken a spherical capsule, the spherical capsule filled with a phase change material, paraffin phase change material. So this paraffin phase change material which melts when the phase change temperature goes more than 55 degrees centigrade, for which where the a setup has been created. So in the setup, we have blower used to suck the ambient air, which is this air passed over the heater compartment. The heater air is heated to the required temperature. This hot air admitted over the spherical capsule. Thereby, the heat is transferred from the hot air to the spherical capsule, so that the paraffin stored inside of the spherical capsule will start to melt. So we would like to know what is the time taken to change the phase change of paraffin from solid to liquid. Right, this time taken we have analyzed by using experimental method as well as the computational method. So the melting problem, so where the heater is switched on and the incoming air temperature is raised to the record temperature, for which the thermostat which is provided here, that will take care of the temperature rise of the incoming air. Then the melting process carried out during the solidification process. In the solidification process, where the paraffin already in hot liquid form, so at that condition where the heater is switched off, ordinary ambient air blown by the blower over the spherical capsule. So this coolant ambient air, when passed over the spherical capsule, this air will pick the heat from the spherical capsule. Thereby, the liquid PCM will turn to solid PCM. Once again, here where we conducted computational analysis, experimental analysis for the time taken of conversion of liquid phase into the solid phase. So there are two analyses taken here. One is melting analysis, another one is solidification analysis. These two analyses conducted experimentally and computationally. So this diagram which shows during melting process, the blue color which is shown the paraffin initially available full in solid form. Once the heat transfer taken place very closer to the wall, this is a spherical capsule, very closer to the wall of the spherical capsule, the solid paraffin PCM converted into red color form. Red color means liquid PCM, right? So when time marches, blue color portion decreases, red color portion increases. After 130 minutes, we found that there is no more blue color evidence inside of the spherical capsule. It means the paraffin took nearly 130 minutes to convert a solid into liquid. Whereas in solidification analysis, initially where the paraffin in the form of liquid, full, then heat transfer takes place very closer to the wall, where the liquid PCM transfer its energy to the outside air. Thereby, this liquid PCM converted into solid PCM. That's why the blue color very initially appeared in the vicinity of the wall, inner vicinity of the wall. So when time progresses, the portion of blue color increases and red color diminishes. At the end of solidification process, it took nearly 80 minutes. So nearly 80 minutes where all red color liquid PCM turned to solid color, solid form of PCM. That's a blue color appeared everywhere. So this is the computational analysis. So the experimentally also, where we introduced the enough thermocouple instead of the spherical capsule. Here we inserted thermocouple inside of the spherical capsule, and we monitored the temperature of the PCM. When the phase and temperature reached by the PCM, that the time taken which is monitored and compared. So here the diagram shows the temperature of PCM during experimental method and the computational method. So where in this paper we pointed out what are all the reason for difference in temperature of experimental method and the computational method. So we justified the difference in temperature, and we compared this melting result, solidification result by conducting two different experiment separately. So this diagram corresponds to solidification process. For solidification process, we maintained the ambient air consistently 35 degrees centigrade. For melting process, we maintained a temperature of air at 75 degree consistently in the entire experimental process. So the same problem we extended by we have taken into account the fin. So the fins are introduced inside of the spherical capsule. So the earlier problem was a spherical capsule filled with fin, filled with paraffin, but no fin configuration. But we have taken two more configuration. One is a circumferential fin, another one is orthogonal fin, right? The same quantity of PCM taken into the three same size of spherical capsule, and the paraffin filled in the spherical capsule, and we conducted analysis, computational analysis as well as experimental analysis also we performed. So it is a very much known engineering fact that the introduction of fin obviously increase the heat transfer rate because of more surface area available. But we would like to know which fin configuration. I mean circumferential or orthogonal. We maintained the same surface area of circumferential fin as well as orthogonal fin. So we would like to know which orientation is better in terms of quick heat transfer rate to the paraffin or from the paraffin, right? For which we conducted a computational study. So as like here, so this first set of picture are shown for a plain spherical capsule configuration. So this is circumferential fin configuration. This is orthogonal fin configuration for melting process. Again, the same reason, change of blue color to red color, right? So blue color solid paraffin and red color liquid paraffin. So at the end of phase change process, all the blue color turn to red color. So but there is a different time taken because of the introduction of fin inside of the spherical capsule. And likewise, so here the solidification also performed for plain capsule, circumferential capsule, and orthogonal fin capsule, right? So we compared all these results, and these comparison plotted shown in this picture. So we conducted experimental analysis separately, and we validated computation results along with the experimental results. So the picture shows that so the melting process. Okay, so here the first two bar chart which shows no fin configuration, and this is circumferential fin configuration and orthogonal fin configuration, right? So and this is for melting process and this is for solidification process. Again, so from this by referring this picture, one we can conclude that the presence of orthogonal fin right took very much lesser time to transfer heat from air to the paraffin or paraffin to the air when compared to any other configuration. So for the orthogonal fin orientation, which is a good orientation when compared to circumferential fin configuration. So this is where again we are checking the same experimental setup here. Same experimental setup. We fabricated a 3 spherical capsule. One is plain, another one is circumferential, the third one is orthogonal fin. So for the same 3 spherical capsule, we conducted the similar kind of experiment and we compared all the results. So this is a phase change problem which we have analyzed by using the computational method. So these are all some of the work which we have performed by using the computational method. So this computational method obviously which gives more information when compared to the experimental method. So before start of any experimental work, so it is inevitable to start our problem by using computational method. Once you get the favorable result by varying the flow conditions and the geometry conditions, once you freeze the flow and the geometry conditions effectively with the help of a computation analysis, then finally where we can go for the experimental method. In this way, where we can save our previous time as well as the cost of the cost in terms of development of experimental setup. So that is the advantage of the computational method. That's why most of the industry they use a computational method in order to gain the good advantage of save in time and save in cost. That is the benefit of the computational method. So I think with this time allotted, I would like to stop. There are many more work which we have performed, but as per the time allotted, I would like to stop my lecture here. So the audience, if you have any specific doubt on this, the introductory aspect of a computational method, I would like to answer for your queries.
Yes, sir. Yes, sir. Sir, thank you so much. First of all, the fundamentals have been clearly explained.
Yeah, thank you.
Yes, sir. And so the one of the important concept which cannot be understood by all is grid independent study and the convergence analysis.
Okay.
It was explained in a nice manner. So even the layman can also easily understand the way in which you have explained. So first of all, very thank you so much for explaining nicely, sir.
Yeah, thank you.
And the fundamental, what is the need to go for numerical simulation from experimentation, and what is the necessity have been explained thoroughly. I think this will be useful to the students to do their final project in a very good manner, and for the faculties this will help them to go for better classroom teaching, and for researchers certainly this will be useful to because whenever we submit the research article, first they will ask whether they have conducted any mesh independent study or convergent analysis like that. The first question will be, so this will help them to do in a better way. Thank you so much, sir, and for our valuable time.
Yeah,
And
thank you.
Swapna, you can ask the questions from the chat box.
Excuse me, sir.
Yeah,
The question is asked by Dr. Bhagavati Perumal.
yeah.
What are the different applications of CFD software?
Okay. Different softwares.
Applications of CFD software.
Yeah, there are different software packages are available, right? Many of the software, as I said, many of the software which works a finite volume method. So for flow related flow heat transfer mass transfer related problem, where we can use ANSYS Fluent, which we use here ANSYS Fluent package to solve flow heat transfer mass transfer related problem. Apart from that, where we can use a open form. Nowadays open form, people started to use a open form software and Kamsal software. There are on the Star CD particularly used for combustion applications, where people use Star CD software. There are many softwares are available, but each software for my understanding of this computational fluid dynamics, like where nowadays it is better to use a open form when compared to other softwares, because where more options are available in open form, and these are also like easily where we can learn this open form software, and we can enjoy the benefits of open form when compared to other related software. Since this is openly available, that's why people, our students also, they started to use the open form. Apart from that, when you use a licensed software, anything Star CD or ANSYS Fluent, Kamsal, right, whatever it is, where we can use, there are many softwares are available, but many of the softwares which works are based on finite volume method for flow related softwares.
Thank you, sir.
Yeah.
The next question by Mr. Vasant Kumar. Is it possible to do thermal analysis on FSW using CFD?
I think FSW means friction stir welding, I guess so. Yeah,
Yeah, sir.
it is possible. It is possible, right? See, the welding applications, like where already where people performed by using this computational fluid dynamics concept, it is possible.
Yes, sir. I want to add one point with this. Yes,
Yeah.
sir. So it is highly possible to go for numerical simulation of FSW. Lot of research articles are available.
Yeah.
So as the one who had done research on welding, I can say that. So you can go for finding research article. If anything else, you can approach me also.
Yeah, it is possible.
Yes,
Yes.
sir. Thank you, sir. Thank you.
Yes, yes.
Swapna, next question you can ask, sir.
Okay, sir. The next question by Mr. Ail. Sir, can you kindly brief something about epsilon and omega models?
Pardon, your voice is not clear. Experimental?
Sir, can you kindly explain K epsilon and K omega model, sir?
K epsilon K omega model. Like, see, these are all turbulence model. Like most of our like the basic research oriented problem, like the K epsilon, where this K is one equation, epsilon that is another equation. Like these are all like there are two parameter, K epsilon and the K omega. Like the flow related problem, I mean these are all like how the energy is transported from large lump of fluid to the small lump of fluid, right? So how this energy transported and how the energy which is dissipated successfully, right? So that's why one is transported for K, and how it is dissipated, that is for epsilon. That's why there are two equations, K epsilon and K omega equation. There are different models are available, but for state flow problems, I mean, say for example, I could say if the flow passing through a straight tube, say for example, there is no change in flow direction at all, where we can go for K epsilon model. K epsilon model. So this, as I said, two equations additionally solved in addition to governing equation, right? So one is how the energy is transported, and another one is how this kinetic energy which is dissipated ultimately, right? During transformation from large lump of fluid to the small lump of fluid in the form of viscous dissipation. So to deal this information, two equations taken into account. One is K equation, another one is epsilon equation. But for K omega equation, which is applicable when the flow, if it is not a straight one, so if it is having a more change in flow direction, right, where instead of K epsilon, where K omega model, which gives more accurate approximate answer when compared to K epsilon. So for state flow problem, simple, where you can rely upon K epsilon. For the flow complex flow problem, where we can use a K omega model.
Yes, sir. Thank you, sir. Thank you.
Yeah.
It was explained nicely. So, so very good fundamentals. So, as of my knowledge, so one of the best class I have attended to learn about fundamentals. Even though I am in the CFD field for about more than 8 years. So, one of the first fundamentals. Certainly, this fundamental will enhance the knowledge of faculty, researchers, and students community, sir.
Okay.
And thank you so much, sir. Thank you so much for joining with us. So we will.
Thank you for the opportunity given by the CIT management, and thank you for the opportunity given by Department of Mechanical Engineering.
Thank you, sir. Thank you so much, sir. We will meet you sometime.
Thank you. Thank you. So can I quick?
Yes, sir. You can close your session, sir. You can.
Yeah, yeah.
Straight away, you can close your browser, the particular tab.
Okay. Okay.
Yes, sir. Thank you, Swapna, for your. Swapna, you can. Thank you. Yes. Participants, thank you so much for your valuable time spent with us for learning the fundamentals of CFD. I hope this is one of the the best class on fundamentals of computational fluid dynamics. So, fundamental analysis and computational fluid dynamics are not easy to understand easily, but the way in which Dr. Kumaresan has explained is very good, and it is best to understand the fundamentals from this lecture, and also how to approach the problems and how to compare the results. So he had explained in a nice way. So as far as Chennai Institute of Technology is concerned, so we have a special center to carry out these computational problems. We are good in computational mechanics, and we have very good computational softwares of research versions like Abacus, ANSYS. So we have research versions to carry out the computational mechanics, and so the researchers, those who are willing, those who are in need of any help to get the things from computational mechanics, you can approach us. You can approach me, or you can approach the Department of Mechanical Engineering to clarify your doubts in as far as computational mechanics is concerned. So we have specially established a center called Center for Applied Research, which is purely working on solving problems of computational mechanics. So we have the capability to solve any problem on computational mechanics. Like, so we are solving fluid flow problems, heat transfer problems, and structural problems. The researchers who are willing to get the help, you can approach the Center for Applied Research from Chennai Institute of Technology to get to have a assist from us. So the other center, especially, has been, that is COE, has been, Center of Excellence has been established in collaboration with Haritha TechServe to carry out the problem in design and ergonomics and any robotic analysis. So that also is possible if you want to get any help from Department of Mechanical Engineering, Chennai Institute of Technology. And then, so please keep on visiting our institute website, chennai-technology.com/webinar or chennai-technology.com. Else, Chennai Technology in Facebook, LinkedIn, Instagram, and Twitter will help you to understand the further forthcoming webinars. And so we are conducting the regular webinars. Along with this regular webinar, faculty development programs also being conducted in the next week. So faculty development programs on sustainable smart cities is going to be conducted by Department of Civil Engineering. So 10 experts have been called from different eminent institutes and research organizations like IITs, NITs, and NHPLER, NHPTR, and government research, government organizations. So that will be very big learning for the faculties, those who want to learn the things on sustainable smart cities. And this is not only for the faculties and the students of civil engineering can also register to understand the phenomena. And for the mechanical, mechatronics, and other these things, other students, and 2 days international seminars on advances in materials and manufacturing scheduled on 18th and 19th of this month. So eminent professors from NUS, National University of Singapore, and Cranfield University, UK, and the NITs and IITs are going to deliver their expert lectures. So those who are willing to learn the different technologies and materials and manufacturing can register for this workshop, 2 days international seminar, and you can enhance your knowledge. And this will be highly useful for researchers, those who are working in materials and manufacturing, because the professors, those who are going to address from the NUS and the Cranfield universities are the well-known professors in their particular field. And as it was said earlier, the 2 days international conference on advances in materials and its applications have been scheduled on September 25 and 26. So all the accepted papers are going to publish in the Institute of Physics, Material Science Engineering Proceedings, which is indexed in Scopus and Web of Science. Those who are willing to participate can submit your abstract from now onwards. And this will not be only useful for the mechanical and mechatronics faculties and students. This will also be highly useful to the faculties from the electrical and electronics also, electrical electronics and electronics communication also. Because nowadays electronic materials are booming like anything, research and electronics are booming like anything. So the work on electronic materials also can be submitted. And the civil engineering faculties and students, those who are working on materials and various construction materials, can also submit your articles to these particular conferences. And for electrical faculties, so a lot of works are going on what we call solar panel materials, solar panel constructions. So the works on particular these things can always also be submitted and can get published in the particular conference. And so Thursday, this is one of the very good webinar is going to be addressed by Dr. Ramesh L. Gowdas, professor from IIT Madras, on tips of article searching. Okay, so searching the correct article is an art. So when you get into the search of particular article is like an art. Okay, so that thing will be addressed by Dr. Ramesh L. Gowdas on Thursday, 9:30 to 10:15 and 9:30 to 10:45 a.m. So that will be very good learning. Those who have not registered, you can go out for registration. So this will not be useful only for engineering faculties. This will be useful for all the educators, not only for arts and science college, pharmaceuticals, and architecture, and all the colleges. It will be highly useful for the school faculties also. The faculty, because nowadays the research on education and research is booming like anything. So the faculties are teachers, those who are working in school also can get benefited through this wonderful webinar. So thank you so much. Please visit chennai.technology.com/webinar to understand more about 40 webinars. Thank you so much. We will meet on some other webinars. Thank you.